Hi everyone! Today I would like to talk about my favorite mega numbers. They are actually numerators and denominators of certain rational numbers, and they are the solution of a very nice problem. The problem can be stated in this way. Suppose you have two cubes, one with size length 2, one with size length 1. Of course, the sum of their volumes is 9. And you may ask yourself, there exists another pair of cubes such that their volumes is, of course, 9? Well, before we start, we need to talk about what kind of solution we are looking for. The first thing is that we need a positive solution, of course, because length needs to be positive. And secondly, we need a rational solution, if you think about it. Okay, the problem can be translated in mathematical terms in this way. We need to find rational positive solution to this cubic equation right here. And we will use a trick, also known to Fermat. The idea is that if you have a rational point over a curve, it is easy to find another point. So, let me draw a pictures of this curve. This is our cubic, and the idea is that if we have a rational point over a cubic, and we draw a tangent line from this point, if we find an intersection, then the intersection point will be also a rational point. We want to prove that CD is a rational point. We will start by writing the equation of a tangent line to this curve in function of the tangent point AB. And if we plug it in our cubic equation, we will get a polynomial. The roots of this polynomial, of course, will describe the intersection. And two things are important of this polynomial. First one, it's a rational coefficient polynomial if AB is a rational point. And this is true because if you expand this cube here, and you will see that only fraction and power of A and B are involved, so it will be a rational coefficient polynomial. And secondly, the roots of this polynomial are AAC. Why? Well, because an intersection, we have an intersection in the tangent point, and so we have some kind of a degenerate solution, and so two roots will be AA, and of course the third roots of this polynomial will be the x-coordinate of our intersection point. We will now prove that C is a rational number. We are going to use Vieta's formula. I think many of you know what they are, but let me remind you. Essentially, they are relations between coefficient and the roots of a polynomial. And in the case of a third degree polynomial, like this one, we know that the sums of the roots, 2a plus c in this case, is equal to minus s over t, where s is the coefficient of x cubed and t is the coefficient of s squared. So, what's the point here? Well, minus s over t needs to be a rational number, because of course s and t are coefficient of a rational coefficient polynomial. And 2a is also a rational number, because we suppose that. This will imply that c is a rational number. So, we have just proved that the x-coordinate of our point is a rational number. But what about d, the y-coordinate? Well, the same argument applies. The idea is that if we isolate x from the tangent line and we plug it in our cubic, we'll find a third degree polynomial in the variable y, but the solution is the same. We will find that also d is a rational number. So, indeed, CD is a rational point. We have just defined an algorithm to find another rational point starting from a pre-existent rational point. And we will reiterate this algorithm to find our actual solution. I have prepared some pictures to illustrate this process. The first thing that we have to note is that we already have two trivial rational points over this curve. They are 1, 2 and 2, 1, as you can see. And if we start in the 1, 2 point and we draw a tangent line, we will see that we actually find an intersection. And we know that this intersection is a rational point. We don't like this solution because one of the coordinates is negative, so we don't like that. But in this case, we can reiterate the process. This is actually a rational point, so we can reapply our algorithm. If we do that, we will find another intersection, as you can see. And again, this solution will not be suitable for our purpose, because, well, one of the coordinates is also negative. We can repeat this process another time, and finally we will find a solution. As you can see, the numbers grow very, very rapidly. And that's because if you do some calculation, you will find that the third roots of our polynomial, so the one that describes the intersection, will depend on a very large power of a and b. So numerators and denominators in the reiteration of this process will grow very rapidly. I will be completely honest with you, these numbers are not so special, but there is something interesting about them. In particular, they are the first solution you can achieve reiterating the algorithm the fewest times. What I mean by that is that you will not find another rational positive solution using this method with less than 3 steps, like in this case. So I think they are a little special for this fact. And I hope you like this video. Thanks for watching.